Okay, welcome everyone to this continuation of what are my favorite theorems. As usually, right, my favorite theorems. So take everything with a grain of salt. Actually, today I don't want to even talk about any theorem at all, but I want to tell you about kind of a philosophy. The philosophy or the so-called strong law of small numbers. That's not really a theorem you want to write down. You will see it, but it's a lot of fun, and it's very important to remember and practice. It's basically the mother of all math puzzles, or maybe the mother of all puzzles in general. So it's kind of the idea that if you have a small sample, then whatever you measure about the small sample can be wrong, it can be right, it can be misleading, it can be absolutely the correct idea. Everything is basically possible. You can't tell by looking, right? In contrast to the law of big numbers, which probably all of you know, like if you have a big enough sample, then whatever you measure about the sample is true. That's kind of the opposite. If you have a small enough sample, well, the opposite of if you have a big enough sample and you measure something, then it's true. It's not if you have a small enough sample and you measure something, then it's wrong. But it's rather if you have a small enough sample and you measure something, then you still can't tell. So be prepared for a lot of math puzzles. Uh, Among those will be some of my favorites. So we start with Moses puzzle. So the so-called Moses circle problem. It's a very easy idea. Okay, you just draw a circle. Here's a circle, and um, you ask about the number of faces you get by dividing the circle. So you choose n points on the boundary of the circle, and you connect them by arcs. Basically, that's what you do. So if you just have one point, there's nothing to connect, of course, and you get one face. So if you have 2 points, there's only one arc. You can connect them by one arc, and as you can see here, you get two faces, and so on. 3 points, four faces. 4 points, eight faces. 5 points. Here you go. And you get 16 faces. And if you look at the pattern, it really looks like, well, the next number will be 32, right? Prime powers, powers of 2. So 2 to the 0, 2 to the 0, 2 to the 1, 2 to the 2. So always one lower than the number of points you have chosen. 2 to the 3, 2 to the 4, and so on. So you would guess the next one is 2 to the 5th, right? But it isn't. The next one is 31. And the small glitch that comes in here, the small um, uh, footnote in this puzzle is that I don't allow those intersections of three lines, basically. So whenever three lines intersect, like here in the middle, this is not good. You have to replace it by something like this, like on the other side. That's the only assumption I do. And you easily might not read that. And Moser asks, okay, what now is the sequence of numbers? And up to the first, well, whatever, five, you never see those triple points, so you don't care. And it's kind of obvious that the sequence is 2 to the n, or 2 to the n minus 1 to be precise. But it's not. For the hexagon, here 6 boundary points, you will see, well, the first triple point, if you just connect them in a stupid way, the first triple point, and you kind of have to resolve that, and that results in the loss of a face. So you only get 31 faces instead of 32. So you were fooled by the small sample of just 5 numbers. Right? Although, really, if you look at the pentagon example here, there's no real reason to expect that this will go wrong. You're just completely fooled by the small numbers because you kind of forget that there might be a triple point that you need to resolve. It actually is even worse. We will see that later. But for now, just you take 5 examples. You see an obvious pattern in huge quotation marks, right? Um, and it's just not true. And that's the strong law of small numbers, Really, that's what it is. So basically, here are a few more examples of that type. One of them, on this slide, one example is actually true. One of them is a true pattern. And I leave it to you to figure out which one. But let's have a look. So you take a sample of 1, 2, 3, 4, 5, 6, 7 numbers here. So 31 and so on. And all of them are prime, right? So obviously, if you just have a 1 and then a lot of threes, all of these numbers are prime, right? Well, probably not. There's a statement about prime numbers. Statements about prime numbers, if they're not related to logarithm, they are probably wrong. So this looks to me like a wrong statement, although the first 7 terms look pretty good. This is still the strong law of small numbers because, well, maybe I have seen enough examples involving prime numbers that I can tell that this is probably not true. But still, it looks like it wants to be true. Here's a second one. Um, so just some binomial expansion. And well, if you think about it for a second, this just has no chance to be true, right? Although you take 3 numbers and it looks pretty well, a small sample and it looks pretty good, this should break at one point, right? For a very easy reason. If it wouldn't, well, then you would have seen it in some textbook before because, well, binomials, right? So by expressing those powers, and you have a shortcut for that, 3, 5, 7. So next one would be x plus y to the 9. If you would have a shortcut, that some textbook would have those formulas inside. But people might still be deceived by the first 3, as in the first example by the first 7. Just kind of experience tells us that nah, the first 2 don't really have any chance. But then come the last 2, and they are kind of the same flavor, but now my experience completely fails, right? To me, both look like they could be true or could be false. I don't know how you feel. So the first one is this funny sequence. So you take 1 plus the square numbers of the previous ones. It's a recursive sequence. And you divide by n plus 1. So an plus 1 is the sum over all previous entries, 1 plus a0 squared plus blah, 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 plus an to the squared. And then you divide by n plus 1. And you will find out that all of these are integers. All of these are actually integers. Up to the at least 9th entry, this is the last one I computed. Is this now a fluke or is it actually true? I can't tell. I have no idea. Just from looking at the sequence, I have absolutely no idea. I might be fooled by the strong law of small numbers here, because to me, this looks like something that could be true. If you just rewrite this expression good enough, then you might be able to see that it's divisible by n plus 1. Similarly, the last one, if I just look at the problem and I look at the first, 12 entries, I can't tell whether this is true or not. Right? The strong law of small numbers has taught me I should be careful here, and I have nothing from my experience that could tell me whether this is true. So let's have a look. It's very easy idea. So you take the notoriously complicated function x to the x, you take the nth derivative of that, so a delta, not a 2, nth derivative of that, and you evaluate it at 1. Okay, good. Something you could do. And it seems like this is always divisible by n. So this n is derivative that you take seems to be, and evaluate at 1 seems to be always divisible by n. You write down the numbers, a mod n, and well, you get some numbers, but it seems to be it's divisible by n up to the 12th entry, the last one I've computed. And again, could be true, could be false. I have no idea by just looking at these numbers. Me personally, no clue. Could be, could not be. And as I said, one of these 4 facts is actually true. It might be one of the latter 2. Maybe you want to give it a shot. And one of them has a surprisingly different pattern from what I showed you here. So one of these actually has a pattern, but not the one I just promised you on this slide. Just a different one, a very surprising one. So it's a lot of fun to investigate those 4 problems. So two of them are easy, as I said, and two of them are, let's say, interesting. But just from the small sample, for all of the four, if I wouldn't have had whatever 10 years of math experience, I basically couldn't tell. Right? Could be true, could not be true. I have no idea. Right? That's the strong law of small numbers. Just don't trust um, examples with few entries. Don't trust puzzles. Puzzles are there to puzzle you. Here's another one of my other favorite small number coincidences. So you take Pascal's triangle, here you go, and you take its entries mod 2. So you get only entries 1 or 0, depending whether the entry is even or odd. So the black boxes are 1, the white boxes are zeros, and that's Pascal's triangle mod 2. And you would guess, okay, it looks nice. Maybe it's related to something in number theory, maybe not, but it certainly looks nice. But here comes something that's just a little bit puzzling and it's very funny. And well, it's not quite clear whether it's a fluke or not. So let's have a look. So what do? So you can ignore the first one. The first one is just for illustrations, but basically what you can do now is you can look at the row. So look at this row, for example, and you can read the number that you see in the row. Um, you can read the number as a binary number. So 1 plus 0 times 2 plus 1 times 4 plus 0 times 8 plus 1 times 16 plus 0 times 32 plus 1 times uh, uh, 64. You add those things up, you get some number, 48. So let's do this one. 1, so this is 1 plus 2, you get 3. This is 1 plus 0 plus 1, you get 5. Uh, so 1 plus 0 plus 4, you get 5. This is 1 plus 2 plus 4 plus 8, you get 15, and so on. So just look at Pascal's triangle mod 2 and pretend that each row actually is a binary number. So you get this list of numbers, whatever they are. I've highlighted some of them for you. I leave it to you to figure out why. But anyway, so you get this list of numbers, and let's ignore the number 1. So you get 3, 5, 15, 17, 51, 85, and so on. And this continues, of course, up to infinity. And it turns out that if you enter this sequence, for instance, in the list of integer sequences, you get a nice result. This number list is a number of the regular polygons you can construct by a ruler and compass. Classical result by Gauss. Well, basically by Gauss. So the regular polygons with an odd number of sides that they can construct by ruler and compass apparently appear in Pascal's triangle mod 2 in this funny fashion. So you might ask, is there any relationship between those two, right? Some classical problem from Euclidean geometry, regular polygons that you can construct with ruler and compass, and something that looks more like number theory, like, well, certain binomials which are divisible by 2. And I won't tell you the answer, whether there's a relationship or not. Maybe you can think about it for yourself. But at least there will be a link to the answer in the description. So don't worry. But it's again a nice puzzle. So is there any relationship? This is more like these are more like little puzzles here. So this is a puzzle, kind of small coincidences, and this is kind of thing that should make you think. So is there a relationship now? Am I up to something, or is this just a coincidence of small numbers? As I said, I leave it to you to decide, but the link to the answer is in the description, as the link to the answers to all the other puzzles I presented so far. And the inventor of this name, strong law of small numbers, is Richard Guy. Link to his 2 papers in the description below. Very readable, beautiful. 80 puzzles like I just told you about, of the same kind, together with solutions and references. Brilliant, absolutely brilliant. And basically what he's saying is something that is so applicable to mathematics and real life that I really wanted to make a video about it because I love it so much. So he basically says there aren't enough small numbers to meet the many demands made of them. So basically, every statement for every small number, there is a statement which holds up to that number and then fails. Right? Don't trust. You can't tell by looking. Don't trust small samples. The strong law of small numbers here is the first of his two papers. As I said, link in the description, extremely readable, read it. Yeah, so that is a strong law of small numbers. Absolutely beautiful philosophy to keep in mind, very important. Don't trust your intuition when it comes to whatever sequences, geometric patterns, or whatever. It can always be false. In particular, I was very, very puzzled by, let's go back to Moser, by Moser's puzzle, because if you do this for the 10 gun, so here 10, by the way, beautiful picture, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I haven't resolved any triple points yet. So what you would expect is that you should get 2 to the 9, which is 256. That's what I would expect naively from what I did before, up to the 6 gun. Right, up to the 6 gun, that actually worked pretty well. So the 6 gun had the 2 to the 5th number of faces, ignoring the triple point here in the middle. But the 10 gun, ignoring all triple points, does not have 265. It has 230 faces. I leave it to you to count. There's actually a very sleek way of doing it. You can cut this picture. It has a tenfold symmetry, so you can cut it in 10 equal pieces. And then you just count 23, which is much easier. Anyway, so I was very puzzled, like what 230? I would have expected in this picture to have whatever, 265. But no, you do get 240 and 230. And it gets even more puzzling. So this Moser puzzle is really amazing. Has a lot of surprises. It gets even more puzzling. Namely, I claim if you now resolve all the intersections, like this one here in the middle, and here's another one, for example, here's another one, um, and so on, here's another one, and so on. If you resolve all of them, you actually do get the number of faces you would expect from the picture when you don't resolve all of them. And yeah, I mean, now actually, honestly speaking, if I see this one, I have no idea what the next one is. So now the 11th Moser circle, what is it? If it with or without intersection, what is it? I have no clue, and I would need to sit down and think about it to give a good argument why I expect a certain number. So don't trust your intuition. By the way, I say it again, the answer to this puzzle is in the link in the description. Yeah. Anyway, so today was more like a talk about kind of the mother of all puzzles. So kind of everything you can ever think of can go wrong if you just look at small samples. It applies, of course, not just to mathematics, but if you just make a whatever, if you ask 10 people a question, does it tell you anything about the whole population? Probably not. You could be right. Your measurement could be right, could be the right answer, could be wrong, it could be anything in between. Just don't trust small numbers. Okay, so that's it. Hope to see you next time.